So I'm going to continue with the discussion of tutorial 3. I'm going to try, I've specifically not prepared for this lecture so that I can make a lot of mistakes, so that I can show you how I'm recovering for mistakes. Obviously we have a worked out version of the solution that you will get access to. But I want you to understand that the goal of today's session, this demonstration that I'm doing now, is I am trying as hard as I can to channel what I want you to do. So I am trying to model today, let's say, a generalized kind of strategy for writing this kind of code that I believe you should be following. So I'm going to keep it simple, and I'm not going to do the full version of the model. I'm just going to do the mass balance part. So I'm going to ignore the component balances for now, just so that the size of the code is manageable. As I mentioned before, I think that that would have been an excellent start. Even when I was solving this problem using Medallica, I started with a mass balance only version and extended it to the component balance. So as I've mentioned before, one of the biggest pieces of advice that I can give you is to solve these problems incrementally. I'm sure most of you can agree that very few of you have ever just read a problem, started at the top, written out the solution, without kind of thinking about, okay, what's the next step now? How does that work? So the way I do it is by trial and error, starting from simple versions of the code and extending that up. So I'm going to map out my strategy here, and let me just go back to the problem. So there's a couple of problems that we have. We know that we've got the full set of tanks that with the description. If you want to see that, you can refer back to the previous video. So I'm going to completely skip the model development part, but I'm going to focus on the mechanism of actually solving this using a Jupyter notebook. Also, I'm going to just be focusing on the numeric version of this. I'm not going to be doing the SymPy version of this. So the first base Python part that we have is finding the steady state, and remembering that I'm just going to be focusing for now on finding the mass balance part. One part that I've added all of this stuff in here just so that I've got some reference in the file. Always write as though you are writing for somebody else, even if it's not a graded project, simply because you yourself will not remember that well what you have done. And so it's very useful to kind of walk yourself through the strategy. So I'm going to just start with adding in some headers so that I know kind of where I'm heading, right? So I've got my steady state calculation, and then the next part is going to be this design part. I'm just copying and pasting here from the problem statement. So this is easy enough, but this means that I don't have to kind of turn back and forth as much. If I were doing this by hand or as a project, I would like to have just space for myself. Now, part of the enabling technology for this is knowing how to work with the different cells. So if you press B, you will insert a new cell below the cell where you are now. So if you go here, you'll see a whole lot of different help references that you can go to. The shortcut keys are there. So basically the pattern that I recommend is that you're pressing escape every now and again to get out of edit mode. You're pressing B to insert a cell below, and that way you can kind of build out your solution as you go. You can also move cells. A very useful kind of idea is to move a cell like this, so I can press X to cut it, and then at some point I can press V to paste it there at the same time. So that means I can kind of move them around easily. And then double D deletes a cell. So you'll get used to using those quite frequently. So I know that I'm going to do my steady state calculation first, then I'm going to be doing my design, and then I'm going to be doing the dynamic simulation. I'm going to take the steady state calculation not like in big matrix mode. I'm just going to do it the simplest way that I can think of, which is to encode the givens here. So I know that these things have densities. So I know that rho x is 1,000, and I like leaving myself little clues here so that I'll know what I'm talking about. Rho y. So I've got my A, B, and C spec'd out. I'm just going to attack this from a CIR-like point of view. So I'm just going to solve the mass balances as the solution occurs to me. Remember, we're doing steady state calculation. So if we look at the diagram, we can see that there are 3 streams coming in, A, B, and C. And at steady state, if we do a complete balance over the entire plant, we can easily see that G has to be equal to A plus B plus C. Okay, so we can just write that down. So that's G is equal to A plus B plus C. Now, I do recommend that you try as far as possible to keep the code as editable as possible. What that means is try and use symbols even if you are tempted. Look at that statement, they see, oh, the density is specified, the flow rate is specified. I know both of those numbers as numbers. The one is 1 and the other one is 1,000, so I know A is 1,000. Right? And I also know B is 800. So I'll just write in A is equal to 1,000 and B is equal to 800. I like having as many formulas in editable form as possible because it does make it easier to just play around. So I wouldn't recommend that you kind of plug in as much as it appears that you would normally do. Also keep in mind that because you're working with the computer, it's really easy to reuse results from previous calculations. So it's not that, it doesn't actually save you that much time. In most cases, it's actually costing you time to copy and paste, say, the same formula twice, if you could have just used that once and assigned it to a variable and then used it later on. Also, I don't think in this problem, and I'm just going to be focusing on the mass balance today, I don't think that calculating overall densities is particularly useful in this problem. I know many of you did it. I didn't find it necessary anywhere to calculate the overall density of anything. The question didn't ask for it. None of the equations that I could think of required you to know the density of any of the intermediate streams. So if you're worried about like how could you possibly have gotten from mass to volume without density, because you know the amount of x and y, right? So if you have a total amount of x and a total amount of y, the only thing you need is the density of the x and y. You never actually need to calculate the overall density. So in fact, like you're just calculating an overall density and then using it to calculate something that you could have calculated in a much simpler way. That's in my mind. Okay, so now we have these givens over here. So most of these translate really straightforwardly. I want to call your attention to the fact that I am taking care to retain correct spacing throughout. You will find that in every programming submission that you hand in, yes?
Wouldn't you be assuming that x and y don't really mix in the tanks? They don't change the densities in the tank, they don't mix.
Yes, remember that was one of the assumptions that was clarified on Slack, which was that we assume that this is an ideal mixture. And so for ideal mixtures, so recall that if you calculated a density and you used a linear combination to calculate the density, you assumed ideal mixing anyway. Right, so it's the exact same assumption, which says that an amount of substance occupies that amount of volume. And if you add two pieces, if you add one part of one substance to another part, 1 cubic meter of one substance to a cubic meter of another substance, you end up with 2 cubic meters. So that's effectively what it means to have an ideal mixture, which means that they effectively, the volumes just add together, right? And so that works with ideal gases, works that way, and some liquids also work that same way. So that's the only assumption that you need to kind of do that the volume trick. So now we're going to do So we've got h is equal to g. I am taking care to keep the spacing right. I don't know why. I don't know if it's a specifically novice programmer thing. For me personally, I find it incredibly hard to read words, for instance, if there aren't spaces between words. And I find it just as difficult to read code when it's been stripped of all its spaces. So I really like having spaces on the sides of operators, spaces on the sides of equal signs, and spaces behind commas. For me, it's like I struggle to understand how you could type a comma which is not immediately followed by a space. So it's like almost like a reflex to me, right? Like I couldn't imagine how that could even happen, but I see it all the time. So I'm just warning you that there is a code style mark on all of your code submissions. And I will be marking you down if your code is ugly. Straight up. It's right there in the rubric. I mark you down. I would like your code at least to satisfy PEP 8. You guys should know what PEP 8 is. It is the Python code formatting standard. So make sure that you follow PEP 8. If you feel that you are unable to do this by yourself, there are automatic code formatters that can do this for you. I feel it's just normal kind of hygiene. It's in the same way that you type spaces after periods when you're writing normal prose. This is like the weird thing. I've never seen anybody hand in written work where there aren't spaces after the periods and after the commas and so on. But everybody appears to be fine with leaving out spaces after commas and after equal signs. And if you think about the amount of time that I've spent talking about this, you can see that this is something that I feel passionate about. Even if you only remember that Carl is weird and he likes good-looking code, just do it if you want marks. So I'm obviously rewriting these givens so that they follow in execution order. So because I'm working in Python, I am executing each one of those lines. I can't simply state that constraint in the original constraint form. I have to actually do the equation ordering. I've left out explicit equation ordering out of the module this year because I think it confused more people than it illuminated. But if you want to go and look in my private YouTube channel, there's a video that I did about equation ordering that tells you kind of what the basic deal is. I think the easier version to understand is that when you are writing code, the code lines have to be sequenced in such a way so that when that particular line of code is executed, everything on the right-hand side is known. And I think most of you have a pretty good intuitive grasp on how to make that happen because that corresponds with the way that you solve problems in CIR. And so I'm not going to formalize it any more than that, except to say that this is kind of these follow directly from those I've just really solved in such a way so that it follows, right? So because I knew that I had A, B, and C at steady state, I could easily with my brain figure out that the total mass balance would give me G, and then from there I can work backwards along the givens. And at this point I have A, B, C, and now I'm just looking for D, E, and F, right? At this point, after having solved for these, so remember I've got G and H now. I've also got J and L. Does that make sense? So now I can, by knowing G and H, I can calculate F because F is simply G plus H. And now if I'm worried that I'm doing this wrong, the nice thing about having these cells is I can check myself. Okay, notice what I'm doing. I'm executing those cells while I'm writing them. Why am I doing this? This allows me to use Python to check that all the right-hand sides are known. If I execute that cell, now maybe I lost track somewhere. And I was like, oh, you know what, do I really have G and H? Yes, I do have G and H. How do I know? Because I ran that cell and there was no error. Okay? Look at how I'm doing it. I'm splitting up into probably 5 times more cells than most of you would use to use that set of givens because I'm trying to get that confirmation I want to run as frequently as possible with what I have to build out my section of certainty about what I know is working in my code. And part of this I'm doing completely in my brain, right? So there's no little light or something that comes up that says this code is definitely fine, but the fact that I've run it up to this point gives me confidence that I know at least what all those values are. I can obviously inspect that and just see whether that kind of makes sense. So I'm looking at that, yeah, order of magnitude, that looks like a number that I could maybe expect. So now that I've got F, okay, so I've got A, B, C, G, H, F, J, and L. Okay, so I'm looking at that like with my CIR mind. I'm saying, okay, cool. At steady state, A plus L is equal to D, so I can now calculate D. Does that make sense? So I can simply calculate D directly from that. Actually, I can't remember. Is it necessary to do simultaneous solution here? I think you can actually work the whole way through without doing any implicit calculations. So D is equal to A plus L. Now who's fast? Who's got the remaining unknowns? I'm thinking it's E and F, right? It's actually only, oh yes, I can do K and I. But I know I can do both K and I through balances on those nodes because those things are known. So let's do K and I. So K is equal to J minus L. And I is equal to H minus J. Right? And then lastly, now that I know all of these in streams, I can calculate E, right? Because now I know that E is going to be B plus D plus K. Cool, so at this point, I should know all of the streams. Cool, steady state mass balance sorted, right? No magic tricks, I don't even have sleeves, right? It's just straightforward CIR, and this is perfectly fine. For this problem, you would gain no special additional marks for using SymPy or using matrix algebra or using any special techniques. There's no kind of extra bonus marks for using difficult techniques when simple techniques will do. So when I ask you to solve a problem like this and say, well, start at steady state and then go from there, I'm not expecting you to use some super weird thing that like I have a special star in my mind on. I just want you to use what works. I used what worked now, just going through it, getting there. Okay, so the next question is, assuming that all three of these tanks are of constant cross-sectional area, so that means A1 is equal, and this works, by the way. So that's a perfectly valid Python statement. It works. So I've just set A1, 2, and 3 equal to 3 meters. And in tank 1 and 2, so we know that H1 is equal to 1. And H2 is equal to 1. And so now we're called upon to calculate the discharge coefficients. So the original problem statement, it says assume flow is proportional to level, right? And so we are given a level, right? So we are given a level that says that the steady state levels are 1 meter. And so we now know from the flow idea, the idea was that we had something like this, right? That was what that line implied to us. We're going to rework that the other way around and just say that K1 is equal to H1 divided by the flow coming out of that tank. And so for the first tank, that would be D. And for the second tank, that would be For the second tank, that would be E. But is that the right way around? No, it's the other way around, sorry. Now notice here, I looked at that and was like, that doesn't look like what I'm expecting when I'm thinking about a flow. All these other flows are in the thousands, right? So why am I not seeing a flow constant in the thousands? And again, this is why I highly encourage you to check your results at these kind of intervals. Okay, that looks a lot more reasonable. That's kind of in the thousands as I expected it to be. So now I know that I've solved that problem correctly. Right. Now I'm going to solve the dynamic part of this problem. So are there any questions right now in terms of this general way of working? So the idea is that I'm working slowly, doing one line at a time in some cases. I'm not trying to be too ambitious to build this code. I'm working quickly, so I'm talking through it. But if I were doing this without having to narrate, all of this would be happening actually a lot quicker than if I'd written a big block of code and made a typo and had to kind of go and debug what exactly that typo was, right? So last piece of thing that I'm going to do is the dynamic problem. So now that we have all of this stuff, model an increase of flow in A from 1 meter to 2 meters, or 1 to 1.5. Assume that the level in tank 3 is also 1 meter at the initial conditions. And we can't assume this HG, JK, JL relationship in our simulation. Now, again, to remind myself about what it is that I'm going to do, control minus will split that cell in 2 parts. So I've just like split that so that it's in 2 parts, so that I've got some space here to do this below. This is now my dynamic simulation part. Right, so I'm going to build the dynamic simulation. Now I'm going to model for you the way that I build functions in the notebook, which is I'm going to start by not writing a function. I'm going to start by having just a block of code. I'm going to check that that block of code works the way that I believe it should be working, and then I will wrap it in a function. Now, I know that I'm going to use scipy.in. So I'm going to calculate scipy.integrate, and I know that I need this function scipy.integrate.solve IVP. So I'm just going to check exactly what is going on here just to remind myself, because I know the ODE int and the solve IVP is slightly different. I'm going to need a function that takes time and y as the input, where y is the state of the system. Now remember, in the dynamics community, when we talk about state variables, we're talking about the variables that are the targets of the derivatives. And the whole job of this function is going to be to calculate all the derivatives of the system. So again, just to keep things simple, I'm going to make a couple of simplifying assumptions here. Most importantly, I'm going to ignore the fact that there are blended mixtures of things, and I'm just going to focus on the mass balance for now. So I'm going to build a system that will be able to do the dynamic mass calculations, but I'm going to assume that the density is just constant at rho y throughout the simulation. At least I've got a kind of sanity check, and since the density of the two substances don't differ by that much, they only differ by about 20%, the results that I'll get won't be completely different. They'll be very similar to the results that I'll get when I actually do take into account the component balance, but it'll give me time to finish within one lecture. Okay, so I know that I'm heading towards a thing that'll take a time and a set of vectors. I'm going to kind of align my nomenclature and just use y as the state. And you can see the reason why I'm so hardcore about using the right words for things is because using the right words for things is the key to understanding what I call manualese. Manualese is the language that is used in documentation. And many of you are not very fluent in Manualese. And so you will recognize this if you rely more on Stack Overflow than the actual documentation of the project. Has it ever occurred to you, why is it that manuals are so useless? And the answer is they are simply written in a language which appeals to me because I speak fluent Manualese, right? You should aspire to gaining fluency in Manualese because that means you can actually use the references that the creators of this function thought were useful to use the function when you use the function. Otherwise, you are damning yourself to always be dependent on some third party to interpret the intent of these functions for you. The one thing you can absolutely be sure of is that every function in SciPy has one of these. Now, I can tell you, as a fluent speaker, these are very useful documentation, right? They are built to help you. If this is not describing your situation, don't blame the designers for writing such difficult documentation. Blame yourself for not being fluent in the language that they are using. And make sure that you understand all the words, right? So this kind of state idea is linked to the words that we use. And I'm trying to kind of align the way that I use these words when we talk about it in the module, in the modeling, and the way that it's used in the documentation, because that's how you can understand what these functions are actually looking for. Okay, so we're going to use solve IVP. But I want to actually understand what it is that this function is supposed to return. So this function is supposed to return the derivatives of the state. And so if we're talking about only solving the mass balance for now, there are exactly 3 natural states that we have to take into account, right? Which is the mass in each one of these different tanks. So I'm going to write a function that enables me to calculate that mass, or that mass derivative, okay? So my target is to get to something where I'm able to do this. So that's just so that I know where I'm heading towards. And I know, now again, in my experience, it's kind of easier to work a little bit backwards. So if I know that I'm trying to get to those derivatives, it means that each one of those derivatives, so let me just get rid of this big block of stuff. It means that each one of those derivatives has to be calculated, and I have to be able to have knowns on the right-hand side, okay? So let's say dm1 dt is equal to a plus L minus d, right? dm2 dt is b plus d plus k, b d k e. And dm3 is c minus e minus I, c plus e plus I minus f, c e I f. Cool. So at this point, I should be able to at least check. Now remember, I'm at steady state. So if I've defined these equations correctly, they should all be 0. Cool. Sanity check. Everything seems fine so far. Now remember, I'm working at the steady state conditions. I calculated them up front. I've written these equations, and right now I know that like those equations seem to check out. They do equal to 0 at this steady state. I'm not going to add the changes quite yet. I'm just going to build the chain for myself that will allow me to calculate each one of those values. Now I know that up front here somewhere, and I'm just going to kind of add this in here, A is a function of time in this simulation, right? So let's for now just say that time is equal to 0, and I can put in a very simple encoding of what this specification means that says at time 0, A goes from 1 to 1.5 cubic meters per hour. So I'm just going to encode that in the most obvious way that I can. If time is less than or equal to 0, then A is equal to 1 times rho x, else A is equal to 1.5 times rho x. Okay, so that's the simplest way that I can see to kind of handle that A specification. Sorry. I'm still getting used to typing these symbols. Right, so there you go. So also notice here, I haven't written the full function. I've written that one block. I've introduced a time variable just so that it will work, right? I've written the if, that works fine. I'm continuing along, and I saw that error. Where was that error? Right there in that block. It's one of the 4 lines that I just wrote, right? What I see too much is I look over the shoulder of somebody and they're trying to debug an error. Now it's a typo, right? It's the same kind of error that I just made here. The problem is that it occurred when they called solve IVP, because they wrote the whole function. They called solve IVP, either because they copied and pasted or they just from memory know this is kind of the form of doing integration. Now they're trying to run solve IVP and the error is coming out in their function. I'm writing the code. This is the real code. This is actually the code that I'm going to use for the integration. But I'm writing it piece by piece, checking each piece so that I know, yes, everything seems fine. Everything is working. I'm working from a known call. Okay, so I need to know how to calculate L and D to be able to calculate that first derivative. Okay, so again, we have to know what we know by the time we start with this function. The function receives the states, right? So the function receives M1, M2, and M3. How do I know the function will receive those 3 things? Because those are the derivatives that this function is returning. And so those 2 link together. So when I am writing this function, the function will be passed a vector that contains M1, M2, and M3. I know this because I'm returning the derivatives. That's what solve IVP is going to be calculating. And so I know that up here somewhere, I'm going to be able to do that unpacking to get into Y. Right? And for now, I'm just going to guess some kind of a mass. So I'm not even going to try. I'm just going to like put some numbers in here. Now, why am I doing it this way? It allows me to have some, now these are going to be the inputs for the function. So these cells here, those cells are going to disappear eventually because I'm going to delete them when I actually run the function. But I'm building up the code that unpacks out of the state vector. I'm building a little bit of a demo to just put that in so that I know that the code below this is going to use those values. Now, if this feels a bit weird to you, this is my process, right? So I'm testing it in process. Now I have to calculate these other values. So I'm just going to assume. So now I'm going to get the flow rates out of these tanks, right? So I can use the discharge coefficients that I've calculated. So D is going to be equal to H1 and E is going to be equal to H2 times their respective discharge coefficients. So D and E are 1 and 2. So remember, I just said let's assume that stuff is always going to be equal to row x just to get started. So I've got V1, H1, and D, and then I've got equivalent calculations for, was that E, right? Yes. Right, we said that H, G, J, and L are just going to stay at their steady state values, which also implies that K and I are going to stay at their steady state values. And so the only things that are actually going to change are going to be D, E, well, actually D and E. So that makes sense. We've just calculated new values for D and E, so we now are able to calculate the mass balance derivatives. Is that cool? So now I know that I've got all the code in place. I can now start wrapping this code, and again, some of the enabling technology here is just knowing how the hotkeys work. So when I press capital M, that will, or Shift M if you want to think about it that way, that will merge these cells all into one cell. And so now that I've tested this code well, I can merge that into one big cell. I can wrap it in a function and now I've got my mass balance function written. I know it works because I've tested each of the parts separately. I know that, like, given the stuff that it knows, it will be able to calculate the correct derivatives. I just need to return this thing that I had at the end here. So this is what I'm returning. Okay, so now I just need to check that it actually works, right? So I'm going to return, so I'm going to calculate the MDT at this T and M. Now that's not going to be 0, but I just want to check that it actually works. Y, okay. So there you go. So now I have, in pieces, constructed the balance function. The only thing that remains is to do the actual derivative. Now I know, for instance, that this will result, if I calculate this at 10, look at this, I'm checking now. If I calculate at 0, I get a different answer from when I calculate at 1. Why is that? Because my if inside that function is changing the flow rate of A based on the time. Now I'm checking this not by repeatedly running solve IVP and all the plotting code and everything so that I can see that the charts look okay, right? I'm building up the small parts one by one so that I know every one of those small parts. And I know I don't need to check the other formulas when I'm calculating just the solve IVP result. So the last piece that remains is now to do the solve IVP call. And so I'm just going to do scipy.integrate solve IVP. So solve IVP, I'm just reminding myself with Shift Tab what the arguments are. So if inside those brackets, if I press Shift Tab, I can see. So it's looking for. Now, I don't remember this stuff completely off by heart, right? I'm super dependent on the built-in documentation because I'm always like, I just don't want to spend the time to memorize that stuff. But I also don't want to take the time to go and Google everything every time I just need to do the simplest stuff. So this inbuilt documentation is saving me a lot of time. So dMdt, so that's the function that I'm trying to calculate for. I want to do a t-span from some previous experimentation. I know that it's about 0 to 10-ish. That's the kind of order of magnitude. So it wants t-span to be a tuple. We've got y0, so I'm going to use my y that I specified when I was testing. Not necessarily going to give the right answer, but at least we can check whether it works. And that's all we need. I can see that these are the values that was calculated by solve OVP.